Welcome to this webinar on ECN's newest software tool for offshore wind farms, ECN Despatch. And thank you for coming. My name is Clem Stock-Williams. I joined ECN 1 year ago after working in offshore renewables for 9 years at the German energy company E.ON. At ECN, I manage the research program for installation and operations and maintenance of offshore wind farms. And I also designed the tool and led the team responsible for building it. Today I'm going to start by briefly describing ECN's background, why we are good people to develop this tool, and then I will explain exactly what the problem is that we are trying to solve and what the software is aiming to do. Next, I will present results from a case study on a real wind farm, and this will also introduce you to the current graphical user interface for the tool. And finally, the goal for us for today's meeting is to raise interest and awareness among the industry and put this tool to use. So I'll explain our ideas for how you can get involved and start using the tool. But of course, your ideas are equally valuable, and we look forward to hearing them. So, is it working? Yeah. So, ECN stands for the Energy Research Centre of the Netherlands. The focus is on helping the world transition to a sustainable energy system. Unlike many of the other national research centres, such as the Fraunhofer Institute, we concentrate on bridging the gap between the university and the industry. We have several units involved in developing different technologies for sustainable energy, and one of these is offshore wind. In this unit, we have around 50 researchers looking at many aspects of how to reduce the cost of energy of offshore wind. For example, controllers for turbines and for wind farms, measuring the wind, energy yield estimation, blade design, grid integration, and of course installation and operations and maintenance. The last two areas are very strongly connected for us, as our focus is on simulating offshore operations and then using those simulation tools to help all the players in the offshore wind industry make better decisions. So that is in installation, of course. Strategy for long-term O&M, perhaps before the wind farm is built, or every few years. How to respond when your turbines fail. And now the topic of today's discussion, the short-term strategy. So I want to start with the question of why are simulations important? Why don't we focus on big data analysis or failure prediction or condition monitoring like many other players? Why is this so valuable? Well, the main point is that simulations allow us a safe and a much cheaper environment in which to evaluate the effect of what could be the result of a decision. So often you'll see that this step is skipped. So a new innovation is designed, and then immediately the next step is to build and test it in the real world. And often this results in some surprises, often negative ones, which could have been anticipated with a good simulation tool. And this is all about understanding the costs and the incomes and the risks of a particular choice. So for offshore wind, some examples of that. Firstly, new vessels, access systems, or designs for foundations can be evaluated using our tools to understand the value they will bring to future wind farms. In other words, we can develop the business case for developing some expensive new technology. Turbine layout and positioning of ladders or platforms on turbines affects the accessibility of wind farms and therefore the downtime. The number and size of turbines affect the reliability and cost. Now, with the industry moving into a period of much more rapid deployment of new technology, the risks are going to be much larger for future wind farms. So understanding those risks and the payback on taking those risks is more important than ever to estimate the financial returns. Next, deciding how many vessels of what type for both installation and operations and maintenance, O&M, is complex and very site dependent. And this is probably what we spend most of our time doing. Budgeting for O&M. This is vital, particularly after the warranty period, when the responsibilities are more shared between O&M or operator and owner, and also wind turbine reliability is entering a different phase. If you overestimate or underestimate the vessel and technician requirements, you will either waste money or store up problems for the future. Working offshore is a very risky business. There's a lot of uncertainties, particularly around weather and reliability, which result in complex considerations when you're trying to design contracts. We can help understand these factors by simulating large numbers of potential future time series, showing what is more or less likely, and allowing companies to sign the right contracts at the right price. However, we're also focused on helping a common understanding emerge among the supply chain, so that it is less about competition and more about collaboration, because this reduces the total cost of energy. And finally, on a daily or all the way to a 6-monthly timescale, detailed plans can be made for all types of maintenance. The better that weather conditions and component health is understood, the more impact this plan will have positively. And this is today's topic. So to summarize, we can use simulation tools to understand uncertainty and risk, and once you can simulate, you can then also optimize. So the next question, apart from why simulation, well, why ECN? Well, we understand that more complexity is only required if there is a need for it and a greater understanding to justify it. So as a research institute, we take the best knowledge available from both universities and companies, combine it with our own expertise, and deliver something practical that can demonstrate value. And that's what I will be demonstrating today. We focus on developing the abilities of our simulation tools and then use those to improve the decision making. So reliability is very important, as is realism. And we are equally interested in solving the immediate problems of the industry, such as daily maintenance planning, as we are looking at how the wind farms of 2025 or 2030 might look and developing solutions for those. Final point is that we're not a consultancy. We're not just looking to sell a software product, and we do work with and suggest other companies and organizations where they can add value. So in summary, we are focused on solving complex scientific challenges, leaving the remaining choices to be the ones specific to your business. Let's move on to today's topic. I'm going to show you a quick overview of the problem. I'm sure it's one you're very familiar with. Here is a diagram, obviously not to scale, of a wind farm. You've got a port and some turbines. Every morning, the manager of that wind farm comes into work, and there are some maintenance activities which are waiting to be performed. Each is of different severity and has different requirements to complete. So maybe the red dot at the top is a failed gearbox. The orange blade at the bottom right is a damaged blade, a reduced performance. And then the yellow foundation at the left is an inspection. Of course, on the wind farm, you have available some vessels, some technicians, and some spares. All of them have different capabilities and uses. And you are constrained by weather, and you will have available a weather forecast, which of course will, and the weather will of course prevent access at different times, as well as result in different amounts of wind farm power output. And the question facing the scheduler is to choose which maintenance activities to complete today, in which order, with how many technicians allocated to each, and with the technicians placed on which vessel. Now, in solving this very complex problem in a practical way, it is important to start by asking and answering a few key questions. These are, firstly, what do I mean by a best schedule? Or what would the wind farm owner consider to be the best schedule? Well, the farm is usually contracted to deliver highest energy availability. So a schedule that results in the maximum energy output of the wind farm seems like a logical first choice, and that is what I will be showing you today. Another choice would be the highest net income. So if we now include the cost of the vessels and technicians and the price of the electricity. This is more now a question for the user, but what do I mean by optimization? And to optimize this transfer plan, this schedule for the day, I mean some process which systematically searches through all the possible solutions to the problem I've just asked in order to find the one that performs the best against that objective, maximum energy output of the wind farm. The word optimization is slightly misused sometimes, which can mean sort of trying different things. When I talk about optimization here, I mean some artificial intelligence solution that can sort through these options automatically. In this problem particularly, there are trillions of possible options, and it's not a realistic prospect for a human to sort through them all and reliably come up with the best on its own. So the tool that I'm about to describe is helping the human sort through those possibilities and find the best. And finally, software is most often not used because it doesn't fit well with the existing workflow, the existing processes of the company. So we spent some time making sure we understood what kind of tool would least disrupt this flow while providing the significant benefits that I am promising. So I will just cover the scheduling process now, which I'm sure you will be familiar with. So at 6 p.m. the night before, or 6 a.m. on the morning, a transfer plan is created. This is this cog at the left. This transfer plan allocates the technicians to teams, gives them service orders, work to do, to complete, and assigns them onto vessels. And this is the choice that we wish to augment with artificial intelligence. So what does this mean for us? This means that the user interface of this tool must be intuitive for the scheduler to use. The system must make it easy for the data required to be put into it. And the whole decision-making process must take less than 30 minutes. So the tool must run in a fraction of that time. Of course, next, the big box in the middle, the transfer plan is carried out. Now, the real weather will be different to the forecast weather, and service orders, the maintenance work, will take a different amount of time to what you planned for. Unexpected things can happen. So when the day is over, and you see the recycling arrows, if you like, the service orders in the system are then updated with the actual amount of work done and an estimate of the remaining work. And then, of course, the whole cycle repeats the next day. So to illustrate the tool, I will now go into the case study. This uses historical data from a real wind farm. The Princess Amalia wind park is located in Dutch waters near Amsterdam. If I zoom in on the location, it consists of 62 megawatt turbines. It's located 23 kilometers from the O&M port. It's owned by Eneco and operated by Vestas. And it has been in operation since 2008. So, I will start by talking about one day in the life of this wind farm, namely 14th of September 2014. And this is the GUI, an example GUI to demonstrate the tool. So at the top, you will see the wind farm displayed, and you will see that 2 of the wind turbines are in red, which means that they have failed. The rest of the wind turbines are operational. And you can see why they have failed from the list of service orders, which is in the box at the bottom right. There are 9 maintenance actions, 2 of which are causing the failures, and 7 of which are preventative or optional. Also in the bottom left, you can see the weather forecast that was given at the beginning of this day. It covers 9 days. Each vertical line is 1 day. And the top shows you the wave height in red, and the bottom shows you the wind speed in black. And what you'll notice, I know it's a bit small, but it's easier to see when it's filling your screen. The wave height is consistently below 1.4 meters, and the wind speeds are higher today, around 8 meters per second, and then for the next few days they fall very low, below 4 or 5 meters per second. So, before we get on to the optimization, let us think about what we'd expect to see in this day. This is quite a simple day. I've chosen it on purpose because you can understand the thinking process. So, we are looking to maximize energy output, which means, of course, that we want to fix the 2 failed turbines as soon as possible. So, the optimum schedule should, if possible, fix those 2 corrective service orders. However, the other service orders will require us to turn the turbines off to do them. And we've seen that the wind speed in the future days will fall, meaning if we turn turbines off today, we will lose more energy than if we turn them off in the future. So therefore, the plan for today should not include any of the preventative service orders, but should complete the 2 corrective service orders. The question is, do we have the resources available to do that? And now the user will click onto step 2, and there is presented the vessels and the technicians available on the wind farm. When you click on each of them, and I've already clicked on one of the technicians, the times in the forecast are then grayed out when that resource is not available. So the WindCat vessel is actually available for all times when the wave height is below 1.5 meters. So if I clicked on that, then it would be completely white. But the technicians, of course, are not available during the night. They have daily work shifts. So those times are now grayed out. And the final step, before we get on to the final step, the question is, what was actually done? So the schedule actually used on the wind farm is as follows. The nearest turbine, the corrective service order on the nearest turbine was fixed, but not the other corrective service order. And what does that mean? Well, in the morning, between 6:30 and 7, the 2 technicians get on board the vessel at the port. Then the vessel travels to the turbine. The 2 technicians transfer onto that turbine, turbine 14, and complete the work. And then they transfer off, travel back to port, and unload or demobilize. So they're home in time for lunchtime. So the question is, can we do any better than that? Well, the third step is, of course, the optimization. So in step 3, you choose your objective, energy loss in this case, and click Run. And then what happens is that it normally takes about 1 to 2 minutes, depending on how many open service orders your wind farm has. And then all the transfer plans that the optimizer has tried are placed in this box, displayed in order of how good they are. Typically, you will get about 2,000 to 3,000 possible transfer plans. Clicking on any of them will then plot the route onto the wind farm map above, as you see. And you can mouse over the different turbines, the different blue circles, and see what the arrival and departure times are. Also, you can export the transfer plan to files by clicking one of the buttons. At the bottom, in the little tool explanation bar at the far bottom, it also gives some idea of the performance of the transfer plan against the objective, so the energy loss that one would expect. Now, as can be seen, the best transfer plan uses 5 of the 12 technicians which were available, fixing the 2 failed turbines and not the others. So, logically, we've been successful. The optimizer has found the plan that was most, we already believed from thinking about it before, would be the optimum. Although you'll also notice that it's chosen 3 technicians for one of the turbines, 2 technicians for the other, and in fact the second transfer plan in the list is simply the same transfer plan but with the 2 service orders swapped round in order, and that makes it worse. So if you remember, the actual transfer plan ignored this other turbine. What is the difference? Has the optimizer perhaps just not found that transfer plan? Well, no, that's not the case. It did actually try it. And here is the estimates of energy loss. So the transfer plan used caused the wind farm to produce about 3 megawatt hours less that day. The little orange bar that you can just about see on top of the green bar is the estimate of the additional energy loss from the failed turbine until it can be fixed on the next day. So to prove that this is a full time domain simulation, which is realistic, here is the Gantt chart for the optimized transfer plan, which I will not talk through, but hopefully it is clear. So it goes and drops off at one turbine, drops off at the other turbine. When that's finished, it goes back to the first turbine, picks up the technicians and goes home. Also includes a lunch break. And at the bottom, the energy loss is re-evaluated now using the real weather. So when I was explaining the process, remember I said, well, the planning happens with the forecast weather, but in reality, things change. And half of that change is due to the fact that weather forecasts are not perfect. So what happened was that the wind speed that day was higher than forecast. So the energy loss is greater. But if we return to the actual plan is still worse. And in fact, it's still worse by about 3.5 megawatt hours. So the optimized plan is still much better than the plan used in reality. So this is only one day. And now I will see how effective this tool is if it is used for a large number of days. In fact, 6 months. So here is the increased energy output now turned into money. And you see the little green bar, that is the 14th of September. And in a minute, I will show you all the other bars for every other day for this 6-month period. So what we've done is every day, we've simply taken the best schedule produced by the optimizer, the best transfer plan, evaluated it against the actual weather, and then compared it with the transfer plan used in reality. And what you can see is most of the days are positive, some very positive, several thousand euros in increased income. But you will also, of course, see that a few of the days are losing more energy, more money. And the question is, well, is the optimizer simply failing to find the best transfer plans? And that is actually not at all the case. What it is doing is choosing to do more of the optional preventative maintenance that day, therefore turning more of the turbines off, in order to reduce the amount of work required in future days, when the energy loss would be greater or the vessel would be unavailable due to weather. So in total, over the 6-month period, this wind farm would have earned an extra 94,000 euros in income. So that's the end of the case study. So I just want to conclude the results from that. When you are trying to find the correct choice and ordering of service orders, combined with the vessels, the number of technicians, considering the uncertain weather forecasts, there are simply too many possibilities for a human to be able to reliably identify the best choice every day. And we want to help with this by using ECN Despatch. We can increase either gross or net income through resource allocation and service order prioritization. Perhaps more importantly, by either performing more tasks today or more tasks in the future. Also, this case study doesn't fully demonstrate the benefits, I would say, of this tool. Princess Amalia is a relatively small, close-to-shore wind farm, which has been operated for a long time with only one vessel. So there's a lot of experience of how to operate this wind farm. However, we have still demonstrated some significant improvements. We've also only looked at minor maintenance operations, so things that can be completed with a small crew transfer vessel. So we can also look at multiple vessels, and we can also look at the trade-off between the energy price, which obviously will discount full power output times. So I hope this has convinced you of the potential benefits of this tool as an aid, a help for the scheduler on your wind farm. So the question is, what can we do? So what do we want to discuss? Well, we want this tool to be used on a wind farm. This tool is not saving anybody any money being used on my computer in historical case studies. So we want to implement it on your wind farm, or we want to work with you for you to implement it on your wind farm. We understand that there is a need to build a business case for this. So we're happy to start with a very similar case study, but using your historical data. And then, assuming this is successful, we would look to link the tool with your systems so that it can be used every day. Now, if you own or operate multiple wind farms, then there are even larger benefits, since it makes sense to then take the tool, redesign it, perhaps, according to your workflow and systems. The user interface, we could make a bespoke user interface. We could allow data sharing with the central office from the local wind farm. Perhaps. These are just options. And as I explained at the start, this is based on a simulation engine, which also works for other timescales, other decision making. So the decisions taken every day could start to link more to the corporate objectives. So more of a connection between each wind farm and the central asset management. How could we achieve this? Well, I would also like to point out that everything I have shown you has been developed since the beginning of this year, so in the first 5 months of this year, although the thinking process has been longer than that. And it has reached the stage already where we can only really develop it further through getting feedback from daily use and detailed feedback from schedulers interacting with it. So we would like to collaborate. A stage-gated approach so that each investment step is approved and we can deliver value. And we would start, of course, with the case study I mentioned. Then we would adapt the software, or help you to adapt the software, to interface it to your systems, or adjust the user interface if you would like it to still be standalone. And once that's successful, a phased implementation in different wind farms across the business. Importantly, if we learn together, we both get greater value. We can implement improvements to the function and the feel of the tool together. Now, there is a lot of development work that has gone on and been put into this tool. However, for the first users, we are not going to charge any sort of software fee. The interaction we see is purely where our time or the value we deliver is paid for, and the effort we put in delivering the tool and adapting it to be specific to your business. And if you would like to discuss public subsidy projects to help with that, we are very open to that. We have plenty of experience writing successful proposals and can help as well. And finally, if you really love the tool and you're thinking about taking further commercialization of this software on, we are open to that discussion. But please be aware that our goal is to help the industry as a whole. So we do need to be careful of that, but we have gone down this route before where it was correct and best for both people. So, thank you very much for your time, and now we are able to answer some questions. So the first question I see is, does the scheduler use an evaluation of the resources used for past tasks in an estimation of the future tasks, i.e. does it learn? The thing that it would learn from is the amount of time taken on previous tasks. So you have an assumption beforehand that a certain service order would take a certain amount of time, and that is obviously uncertain. After you do a maintenance action of that type, then you will know how long that service order has taken in terms of technician time. And so you can update your previous assumption about how long it would take based on the time used. This is not something we have used in this case study because we don't have any maintenance manuals for the turbines. So we can't classify the different service orders completed into groups. Therefore, we've treated each service order uniquely. But in a tool that was implemented, we would use that feature. which optimization technique is used. Let me go forward and perhaps explain the background and Masood's question on optimization technique. So all I showed you so far was this graphical user interface, and I understand that has become a bit of a black box. So let us open up the box. So behind it is what is called a meta-heuristic algorithm. This kind of algorithm relies itself on a black box. So the optimizer tries different transfer plans, and all it learns about those transfer plans is how well they perform against the objective, so how much energy loss they cause. However, the black box is not a black box to us. What happens is that transfer plan is converted into a schedule. So there is a planner that comes up with those Gantt charts I showed earlier, the realistic definition of how objects move around the wind farm, how vessels and so on. That plan is then put into a simulation. So the wind farm is simulated in order to see how much energy loss there would be, and how much everything would cost. Those things are then combined into the solution. So if you have the energy price, the simulator would calculate the energy output and the costs of all the equipment. That would then be combined together to produce you the net income value if you were using that. There is another part of it that then looks at future days. So I talked about this, perhaps I didn't emphasize this enough. It is very important with this type of short-term optimization tool to calculate the cost of things that are not done today, to get full closure on all of the service orders, not just the ones that were done or chosen for that day. And that's what the remaining work calculator does. It looks at the future weather forecast and tries to plan all of the service orders not completed on the first day during that time and estimate how much they would cost. And those things are provided back to the optimizer, as I said. It tries 2,000 or 3,000, and then those results are then put back into the GUI. Question 2 from Masood was about SAP integration. No. We've deliberately not tried to do that because that is in some ways a business-specific thing. What we do have behind this is a set of databases. So it's not just the program that you saw, there's also these databases behind that contain all the static information about the wind farm, so turbine locations, etc., power curves, number of technicians allowed simultaneously on the turbine, and all the dynamic information, so the weather forecasts and the service orders. So that means that we can take this model, this tool, and deploy it into your environment by just linking SAP and any other databases you have to those databases. We don't need to write a link in code directly between the tool and SAP. We just have to link SAP to a set of databases, and that is much easier to do. The next question was, do I understand correctly that you can define your own cost function, i.e. yield loss or something else? Yes, we can define any cost function you like. It is in code, so it would need a small amount of work, but most things are calculated by the simulator, so it would not take long to implement a new cost function. With the discussions we've had from the industry, then energy loss and net income are the two ones that people would look to optimize for. So I would be surprised if something else was more important, but that is your business case, and if it was, then we can implement that, no problem. So back to Mark's question, what metocean data do you need? Is it a forecast and wave-buoy? So in order to do the planning, you simply need forecast, well, wave and wind speed. So wave height and wind speed is the minimum you need. In a future version of the tool, planned for the next few months, we will also consider uncertainty in those values explicitly. But if you don't have that, that's fine, because that's how the tool works at the moment. So it just looks at the most likely future and plans for that. If you have, and we obviously in separate projects we were working on more sophisticated representation of metoceans. So considering wave periods, wave directions, for accessibility, for instance. If you have a good understanding of those and would like the tool to consider these more metocean parameters, then we can certainly work to implement that and make the tool use those things. So currents, more waves, more wind direction, fog, whatever you fancy including. If we have a good understanding, then we can do that. Cloud-based, excellent question. This is on the list. So if I have a list that I've prepared of future developments. First one is net income, and I talked about uncertainty, spatially varying weather, transfer and transit using actual understanding of vessels and accelerations, more weather conditions, different outputs that we haven't yet implemented because they're business specific, and us spending time on this without a customer is not useful. And the last one is implementation in the Microsoft Azure cloud and a web GUI. That is something we want to do. It is something we are planning on working towards over the next year using a project. As I explained, we use external software engineers to do this, so it would be a robust solution, but it is not done yet. It is in our general plan, but it is not yet available. We can definitely see the value of that. Mark's question is, you saw a slide flash past where I overlaid weather with, let's go back, actual. This is for that one day I showed you in the case study, and I wondered if people might have a question about why the evaluation of energy loss with the actual weather was so different to the evaluation of energy loss with the forecast weather. So what you see here is the red dot is the forecast trajectory of wind speed, and the blue line is the actual wind speed. And what you see is what looks like a fairly small difference in wind speed during the first day. That is causing the large change in energy loss because of the cubed effect of a power curve. What you also see is the future energy loss is much greater because in the last 2 days the forecast was very wrong. So if you have to do some work then you're losing an awful lot of energy. So that is the difference. But that's why that slide was in there. How uncertain your forecast is will entirely depend on your supplier and the location. Antoine, can the number of technicians and vessels planned for a wind farm be optimized? Or does the user have to iterate by choosing a different number of each? No. The number of technicians and vessels is optimized by the tool. What you set up in the step 2 is you select which ones are included in the optimization, that's all. So if you want to not allow the optimizer to consider vessels or technicians, it can do that, but it is automatically selected from the choices you give it, absolutely. So for instance, on the 14th of September case study, you saw that 12 technicians were inserted into the optimizer, but the best choice used only 5 of them. So it can choose not to use technicians. I mean, when planning the staff that will be hired and the vessels that will be chartered. Okay, we have a different tool for that. So this tool is focused on taking decisions that you can take on the day. Planning further ahead is really important, and we have an idea for this tool that there will be a sort of historical mode where you can go back in the same way as we did for the case study and evaluate periods of time and see or look at the utilization of technicians and vessels, so that you can see whether it would have been better to have fewer or more technicians or vessels. So you could re-optimize using more or less. Well, use more, put in more, and see if you could have used them. But if you're looking at longer timescales, then we do have separate tools that help you decide how many vessels to schedule to contract for your wind farm, and they are better suited, I would say, to that decision making. The beginning of operations, and we don't know how long correctives take. Yes, so this is what I was referring to before. You would initialize this tool with some assumptions. And when we have the uncertainty considering version of the optimizer, then this will be even more powerful. But even at the moment, you just initialize with your best guess. So an average assumption that minor operations take 2 hours, intermediate operations maybe take 12 hours. It's up to you. We could even provide some estimates from our knowledge and our data background, but maybe you have that knowledge from your other wind farms. But we can help come up with sensible first guesses, and then, as I say, it sounds like a priority then would be to implement the updating system, whereby those assumptions are updated every time at the end of the day. When a service order is completed, the amount of man hours used is then fed back into the database and used to update the assumptions. The last question, does it allow evaluation based on different decision rules? So if you mean optimization objectives, then yes. So at the moment it is energy loss, so minimizing energy loss, or equivalently maximizing energy output, or maximizing net income. And if you wish to have additional rules implemented, optimization objectives, then we can do that as well. But those two were the most sensible. Can you do it in parallel? No, you'd have to do two separate optimizations for the different objectives, and then you would look at the different results. If it is really important for you to do that, then we could implement a comparison screen. Every optimization that is done is saved back in the database at the moment. So what we could do is implement a comparison screen that compares the results of different optimizations, or compares transfer plans against different objectives, and would help you make that decision. But I think that kind of decision would be best, that would be a scheduler's logic, and so it would be good to build that kind of screen for the user. How many days in advance should we have the weather forecast? The weather forecast in this instance was provided at 5 a.m. in the morning. So it's provided twice a day, but the schedule was created at 6 o'clock or 5:30, so we used the 5 o'clock, the latest weather forecast. It's a 9-day weather forecast in this. If you have much shorter forecasts, it may affect the operation of the tool, but we can work around it. Most weather forecasting agencies give you at least sort of 6 to 9 days. So maybe there was a misunderstanding in the question slightly. So both the optimization was scheduled at the beginning of September the 14th in order to plan activities for September the 14th. So the red line you see is the forecast delivered on the morning of September the 14th. So it is the latest forecast. Masood, market forecast is crucial. Yes, if you are using the net income objective, then you must have price information. It is not missing. It's just in this case study we did not use it because Inoco obviously declined to tell us about their market information so we could share it with the world. But it is possible to input it. There is a space for it in the databases, and it would be input, and it's simply multiplied by the energy output at each time step to give you the total income. Could you say something about system requirements? Would I need a computer? Absolutely not. So, as I said, each one runs in a couple of minutes, and this was on a normal laptop. So a cloud-based system would obviously run much faster, and the question would be really how much do you have to scale your cloud-based system? But it really is quite low processor intensive, and we haven't even bothered parallelizing it yet. So it could be much faster. So no, absolutely not. Your normal desktop or laptop that you provide your scheduler with would be perfectly adequate for testing the tool as it currently stands.